Welcome back, guys. It's been a while. Today we're talking about solubility. This is 10.3 notes. Let's dive in. Okay, so on the screen here, we've got an ionic molecule, NaCl, and you'll see that I've got 8 different water molecules on the right side. Notice here with the water molecules, first off, that there's 4 different ways I've rotated them. So kind of each rotated in little 90-degree orientations is what we're calling them. Just means in a water molecule that's rotated. If we look at the salt molecule, we'll notice that Cl is negative. Remember, that's called an anion. And Na is positive. Remember, that's called a cation. And then one of the things that you'll see here on water is that it's got little pluses next to the gray hydrogens and a little negative on the outermost side of the oxygen. That's because water is what we call polar. So anything that's polar is going to have a slightly negative side, and it's going to have a slightly positive side. So that's water. You can see it's slightly negative side, slightly positive side. And that's a good definition for polar. It's going to have 2 sides. One's negative, one's positive. Now, solubility, which is what we're talking about today, is the ability for a solute, that's NaCl in this case, to dissolve into a solvent. In this case, that's water. So based on how well it dissolves, that tells us like it'll have higher solubility if it dissolves well. If it doesn't dissolve very well, it'll have lower solubility. If you take a look at this animation now, very proud of this, you'll see that over time, water molecules will kind of put themselves in between an Na and a Cl molecule, kind of splitting the Na and the Cl up. That's how dissolving actually works on a molecular level. So let's show you that one more time here. There it is. And then what you'll notice here, here's maybe a better picture, is you'll notice that the positive ends of the waters kind of match up to the negative ends of waters. You'll also notice that all the negative sides of water are attracted to the positive Na, and all the positive sides of water are attracted to the negative Cl. And when they do that, water itself, you'll see here in the middle, you've got the negative end of one water molecule attracted to the positive end of the other water molecule. So this is what we call energetically favorable, meaning that water wants to kind of align so that the negative ends face the positive ends. And so it just kind of makes sense that the water molecules would kind of come in between the NaCl and split them apart. So I think that's kind of cool. Hopefully this whole thing helps you kind of see, how exactly does stuff dissolve? What does that look like on a molecular level? Okay, let's talk solubility rules now. The rule is like dissolves like. So what this looks like is it looks like 2 different things. We could have polar solvents or we could have non-polar solvents. If we've got a polar solvent, right, like water, it's going to dissolve polar solutes. The like polar dissolves like polar. Fun fact, we also see that polar solutes dissolve ionic solutes, like salt or other ionic compounds. Nonpolar solvents only dissolve nonpolar solutes. So if you have oil, for example, salt doesn't dissolve very well in oil. Fun fact. So write that down. Solubility is like dissolves like. That's another way to talk about it. Alrighty then, let's jump into some solubility terms. The first solubility term we have is saturation point. So saturation point is the maximum amount of solute that can be dissolved in a solvent at a specific temperature. So the one thing that's important to look at here when we're looking at saturation point is that it has to do with the amount of solute you have, it has to do with the amount of solvent you have, but it also has to do with the temperature. So those 3 things are important when it comes to dissolving something. So if you want to make a amount of solute more dissolvable, you can either add more water to it, add more solvent, or you can increase the temperature. Those are two different ways to get stuff to better dissolve. Now, saturation point is important to know because these three other terms describing solutions all revolve around the saturation point. For example, unsaturated means you're below the saturation point. So let's say, for example, to saturate a sugar water solution, I think it's something like 80 grams of sugar. You need 80 grams of sugar in order for that solution to be saturated. So if you only have 2 grams of sugar in 100 grams of water, let me clarify, 80 grams of sugar in 100 grams of water is a saturated solution. So it would be 80%, or not 80%, it'd be some percentage of sugar by mass. Unsaturated would be if you're below that saturation point. So maybe you have 10 grams of sugar in water. That's unsaturated. Saturated is when you use a lot of solute. You have to be at that saturation point. So if 80 grams of sugar can dissolve in 100 grams of water, a saturated solution would have 80 grams of sugar. There you go. The last thing you can sometimes have, this doesn't always happen, but it sometimes happens, is you can have a supersaturated solution. So for the example of sugar water, what you would do to get above the saturation point is you would have 80 grams of sugar dissolved in water, and then you would heat that water up, kind of boiling some of the water off, and then you kind of you no longer have like a liquid, you kind of somehow have a syrup almost. And kind of the idea is if you then add any more sugar into it, it'll just all start to crystallize, and it will no longer be a liquid, it'll kind of be like a solid, just a bunch of crystals. Supersaturated solutions are very weird. The best example I can give you for an example of a supersaturated solution would be honey or syrup. Something where like over the course of making it, you have to kind of reduce the amount of solvent. You have to kind of boil off some solvent to make it happen. And we'll explore more about honey tomorrow in the lab, so get excited for that. Here are unsaturated, saturated, and supersaturated solutions, kind of a more visual representation of them. What you'll notice here on the top is unsaturated, you don't use a lot of solute. Saturated, you do use a lot of solute. And supersaturated, you have to use even more solute. And once you start to get above that supersaturated point, you'll see here crystals begin to form. You know a solution is saturated because if you add any more crystals, you'll get some of those crystals that just fall all the way to the bottom. So for example, maybe this is a salt particle here up at the top, then at the bottom, that would be the same salt granules just falling down. Difference between supersaturated is you add all these salt crystals and then, these maybe salt particles, and then you get actual, like the whole solution kind of starts crystallizing, and it doesn't just look like they didn't dissolve. It looks a little bit different. Also, you'll see here at the bottom, I've labeled unsaturated as anywhere from very dilute to dilute, and then saturated tends to be very concentrated. So somewhere in the middle between unsaturated and saturated, we would have a concentrated solution. And then saturated tends to be about as concentrated as you can get. If you're in the realm of supersaturated, then you're into the realm of things that are kind of syrupy, that are very, very concentrated. I said extremely here at the bottom. So, yeah, fun fact. Here's a solubility curve. This is how we will solve a bunch of problems. So let's just focus for now on NaNO3 here, kind of in the middle. And you'll notice that the y-axis here is the amount of solute that can dissolve per 100 grams of H2O. And then the x-axis here is temperature. So one of the things you'll notice, kind of a general trend, is that all of these lines have a positive slope, except for NH3. And that's because in general, when temperature increases, solubility increases. Now you might be wondering, why is NH3 downward? Well, NH3 is actually a gas, and all these other solutes are all solids. So solid and liquid solubility increases as your temperature increases, but gas solubility in a liquid decreases as your temperature increases. Think about it like pop. If you have pop on a hot day, or you leave it, if you store pop in like a hot environment, it's gonna get flat quicker. And that's because the carbon dioxide in the pop liquid kind of tends to dissolve or to come out of the solution and just kind of bubble out. So that's what all these graphs are showing, is they're showing as your temperature increases, your amount of solute goes from 70 to 150 for NaNO3 specifically. So at 0 degrees Celsius, I can only fit 70 grams of NaNO3 for every 100 grams of H2O. But if I increase that up to like, let's say 80 degrees Celsius, now I can fit somewhere around 145 grams of NaNO3. So as my temperature is increasing, my amount of NaNO3 I can put in H2O increases as well. Now, to be fair though, I could still have less. This line right here is kind of the saturation point. So for NaNO3, for example, I could still dissolve 10 grams of NaNO3 at any one of these temperatures. That would be fine. That would totally happen. But I couldn't, for example, fit 80 grams of NaNO3 at 0 degrees Celsius. That would be considered a supersaturated solution if I made that happen. So this line kind of tells us where the saturation point is. Anything above it is supersaturated. Anything below it would be unsaturated. Okay, so here are 3 points. We're using NaNO3 here. I want you to label these points, 1, 2, and 3, as either unsaturated, saturated, or supersaturated. Go ahead and try this out. Great, so hopefully you did. Point number 3 is unsaturated, point number 2 is saturated, and point number 1 is supersaturated. Supersaturated because it's above the curve at a certain temperature. Unsaturated for number 3 because it's below the curve. And 2 is considered saturated because that point is right on that NaNO3 line. So that would be saturated. So at the temperature of 50 degrees, for example, 80 grams per 100 grams, that would be unsaturated because the maximum we can fit is somewhere around 115. For number 2 here, it looks like it's right at 115. That's saturated. And for number 1 here, it looks like it's around 135. So that would be supersaturated because it's above that curve level. Go ahead and try the same thing for KNO3. Hopefully you did. With KNO3 now, number 3 is going to be saturated, and then 1 and 2 are both above that KNO3 line, so they are both considered supersaturated. Here are some practice problems. Some of these are just, can you find the points on the graph? So let's go ahead and go over these together. This first one says, how many grams of NaNO3 can dissolve in 100 grams of water at 70 degrees Celsius? So we're looking for the number on the y-axis here, and then we're looking at 70 degrees Celsius. So what we're going to do is we're going to find this curve for NaNO3. We're going to find 70 degrees Celsius, and we're going to just find the points where those two match up. And it looks like it's right around here, right around that 133 mark. So we would say for there, it'd be somewhere around 135 grams. And I'll take a little bit of leeway on these answers if you had a number that was slightly higher or slightly lower. For this next question here, we're going to say how many grams of NaNO3 can dissolve in 50 grams of water? Now, what you'll notice here is that it's the same question as before, but what's changed is my amount of water. So this scale is only good for 100 grams of H2O. If we change it to 50 grams of water, we're kind of cutting the amount of water in half. So that would also cut our solute in half. So instead of saying 135, we would say somewhere around like 68 grams. because we could fit 135 grams, 100 grams of water. Now we have half that amount of water, so the answer would be 68. This is probably the best way I can trick you on quiz questions, is take a problem where it's just a simple, can you read a graph, and turn this into, okay, now we're changing the parameters a little bit. We're changing how much the water is. So if I then quadruple the amount of water, that's going to take this 135 number and quadruple it. So it wouldn't be 135 anymore, it'd be 540, because 540 is 135 times 4. We talked about this a little bit, I kind of alluded to it. How does gas solubility change as temperature changes? As temperature increases, gas solubility is going to decrease. You want to think about pop here. And it also keep in mind that it's the opposite of solid liquid solubility. So I would definitely write this down. As temperature increases, gas solubility is going to decrease, but solid solubility is going to increase. And that's kind of what we've seen if you look back at the graph over here. That's what we've seen with most of these curves. Most of these compounds are solids. They're salts, realistically, so they all increase as you dissolve in water. NH3 is the one exception here where it decreases. Great. All right. Hey, thanks, guys. Go ahead and try out the quiz now, and don't forget to have a great day.